Hello, my name is Robert Toomey, and this is my project presentation for GIS 512, Introduction to Remote Sensing, taking in the spring semester of 2016. Basically, for our project, we are trying to apply some of the techniques that we learned throughout the semester. I decided to apply unsupervised classification techniques to merged reflectivity composite data. So our basic research questions are as follows. 1. Can we apply standard GIS unsupervised classification to CONUS merged reflectivity composite data? More on what that is later. And 2. What type of results can we expect and how can we use this in practice? In particular, since real-time data is most useful in time series, we want to be able to apply these techniques in batch. First, let's talk about the data we'll be using. The National Weather Service has about 160 radars covering the continental United States, or CONUS. This collection of radars is called the WSR-88D network. This stands for Weather Surveillance Radar, and it collects multiple moments or bands of weather data in real time. One of these bands is reflectivity data, and this polar data is collected in dBz values, which stands for decibel relative to Z. Basically, it is a value telling us how much the atmosphere is reflecting the radar, so a severe storm with lots of rain or hail would typically have a higher dBz value. This data is collected in what are called volume coverage patterns, or VCP. Each radar spins and takes a polar data sample at a collection of different angles. This allows data to be used in 3 dimensions from multiple radars to fill in gaps or holes of one particular radar. Also, if radars overlap, weighted techniques can be used to take into account data from each of the radars. This gives a final merged composite reflectivity image. There are some issues with this ground-up approach versus satellite or aerial photos. First, each radar has what is called a cone of silence, where data directly above the radar can't be sampled. This is just because the radar can't tilt up beyond a certain angle. The second issue is that terrain, such as mountains, will block the beam, causing missing data. A final issue can be that the range from the radar center is not as accurate. Our methods are basically as follows. 1. We create a multi-band GeoTIFF image from an internal Woods 2 netcdf data format that has all the merged data ready for us. This data can then be imported into an ArcGIS geodatabase using the Raster to Geodatabase Toolbox. After this, we can clip the CONUS down to a smaller study area, and then we can also run a filter or cleanup pass on the data. For classification, the results seem better if we first remove any major outliers from our data. A dBz range of around -30 to 75 covers most possible data values. We then use the Spatial Analyst Toolbox extension in ArcGIS, which gives us several tools under the multivariate category. The one I was most interested in was the Isocluster Unsupervised classification. This was applied in batch to a collection of images, and then we compared the results at the end. Now we show a simplified flowchart showing the basic flow of how we generate and compare images. We start with converting data, then clipping and filtering. Finally, we loop over the time series of images in a batch model isocluster. Once this is complete, we can compare final images. First, we look simply at the original clip data. Here we show a storm area with simple standard deviation stretching on the dBz values. This is pretty much just the original data for reference. We can see there isn't much detail, especially in the lesser storm areas. The second image we look at is the values with the red, green, blue bands chosen from the stock color key. This is what we typically use when you see an image like this on a television station. Finally, the third image is an example of running the Isocluster unsupervised classification on the original dBz data. In some ways, the human-chosen color key gives us decent results, but the unsupervised classification allows us more flexibility and breaks up data by statistics and ISO boundaries rather than fixed chosen ranges. On the other hand, comparing multiple images in a time series could possibly be worse, since the classification would not necessarily be constant for all the images in the series. In conclusion, we can say that automation of unsupervised classification of merged reflectivity composite CONUS images in software such as ArcGIS or ArcGIS could be a useful way of clarifying or re-examining a weather dataset. In the future, to make this more useful, adding auto-clipping and auto-range filtering into the ArcGIS Toolbox model would make it much more useful. Also, ArcGIS provides a raster to video toolbox that works on JPEG images. Automatically generating storm videos with the resulting classification would give a useful and helpful way of examining the data in practical daily usage. That's it. Thanks for your time.